Okay, this is in this class actually what we will discuss is about the simulated annealing. Simulated annealing is another non-conventional optimization technique. It is included in your syllabus in the third module. It is included, that is simulated annealing, as well as the Tabo search is included. So that's why this came up in our lectures also. So it is the genetic algorithm, as we have seen. It is a population-based optimization method. That is, there is a number of individuals involved in that particular genetic algorithm. That is in a particular generation. But in the case of simulated annealing, mostly it is a single solution based, that is a single individual based algorithm. That is, there are no population of individuals involved in simulated annealing. And this simulated annealing is actually a simulation of a computer simulation or a software simulation of the physical annealing process. The annealing process is actually a mechanical engineering term. In the manufacturing term, the annealing is being used. That is, the solid metal, the metals or the solid materials is heated past its melting point, and then it is cooled back into a solid state. And the cooling is, in the case of annealing, mostly the cooling is done in the atmospheric air itself, so that a very slow cooling rate is happening. So that is, a material is melted, that is, it is heated past its melting point. It becomes the liquid state, that is, it is in the liquid state, and then it is allowed to cool on its own in the ambient air. The ambient air is mostly used just because of the cooling rate is to be very low. When the cooling rate is very low, the solidification is in a specific way, so that particular specific properties of the material, we will be getting specific properties of the material, so that the energy so the molecules in the material will get sufficient time to settle down to its lowest energy point, etc., etc. So that's it. The structural properties of the cooled solid depends on the rate of cooling. So if it is a faster cooling, like if we are dipping the molten metal, or some water is poured over the solid material, or if the container in which the solid material is placed is dipped into the solid, into water or oil bath, then the rate of cooling is very fast. So in that case, the molecules won't be getting enough time to settle down to its lowest energy state. So Metropolis et al. In 1953 simulated the change in energy of the system as it cools until it converges to a steady frozen state. So at its molten state, the material is in a high energy state. That is, the material is having very high energy. High energy in the sense, that when a particular material is in its liquid state, the molecules are moving very fast within that material, within that liquid. In the liquid phase, the molecules can move freely within that material. But when it comes to that is a high energy state. That is, the molecules will be having very high energy. The high energy in terms of kinetic energy or potential energy, etc., etc. So, but when it is cooled, that is, the temperature becomes lower and lower. The material becomes solidified, and the energy of the material, the energy of the molecules become less also. That is, the possibility of its movement becomes restricted because of solidification. So that was simulated in 1953 by Metropolis et al. And in the case of energy, normally we know that the energy is being reduced in all the cases. But in some cases there is a possibility, or there is a probability of an increase in energy also. That is, normally when a liquid material is solidified, that is, it is getting cooled, the energy becomes reduced, that is, the energy decreases. But there is a chance that the molecules, some of the molecules will get an additional energy, that is, the energy of some molecules may get increased, and the probability of the increment of this particular energy is expressed as it was expressed as the probability of delta E. That delta E is the change in energy, that is the increase in energy, that is a specific value of energy is increased. That is, the suppose if the material is having some 10 units of energy, then the probability of it becoming 12 units. So the change in energy is 2 units. So the probability of 2 units is exponential, that is e raised to x. So the e raised to exp means e raised to minus delta E divided by kt, where k is a Boltzmann's constant and t is the temperature at which this particular material exists, and delta E is the change in energy. So obviously, if the energy decreases, then the system moves to this new state. Otherwise, there is a chance, as I said, there is a chance of increasing in energy. That is, this particular state, the increased energy state is accepted only with this probability. That is, if this particular probability is a very large value, if it is 1, if this particular probability becomes 1, then always an increase in energy is accepted. But obviously, this particular value is never equal to 1. It is always less than 1. So it is accepted with this specific probability. And in 19 et al, they suggested using the simulated annealing for optimization, and applied it to VLSI design and traveling salesman problem. That is how this simulated annealing came into effect. It was in 1983. It was first used for solving optimization problems. So the process of moving from one state to the next is repeated for a number of iterations at the current temperature. That is the concept. So when we initialize a simulated annealing procedure or a simulated annealing algorithm, we start with a large value of 100, say 1000 or 100. A large value of temperature, and at that particular temperature we iterate through different solutions. That is, we change the solution and we check whether this particular solution is better than the current one or not. If it is a better one, then obviously we will select it, and if it is a worse solution, that is a bad solution compared to the previous one, if it is a worse solution, then what we will do is we will accept the worst solution depending on a specific probability, depending on the probability. And when that temperature is large, when the value of the temperature is large, the value is depending on the probability is depending on e raised to minus delta E divided by t, k divided by kt. So when the temperature is large, the probability of it being a worst solution being accepted is large. But when the temperature is less, when the temperature is nearing to 0, or when the temperature is nearing to some 1 degree or less than 1 degree, so in that case the probability of it being accepted, the worst solution being accepted, is very less. So that is the condition. So for a particular temperature, we start with a large temperature, and in that particular large temperature we find a number of solutions. And if the solution is better, we will accept it always. If it is a better solution, we will accept it. If it is a worse solution, then what we will do is we accept it with a probability. And so not all the worst solutions are accepted, but some worst solutions are accepted. And then after this many iterations are a specified number of iterations are repeated at the current temperature, then the temperature is then decreased. A sufficient rate of or a difference in temperature is given. So if it is 100 degrees Celsius, if we initialize the temperature as 100 degree, it can be reduced to 90 or 95 or even 99 also. If we are reducing it to 99, it is a very slow rate of cooling, and the number of iterations in each temperature should be very less in that case, if the number of the change in temperature is very less. So then this procedure is repeated until the system freezes into a steady state, and the freezing temperature, that is the last temperature that we decide. It is not always 0, because if we take it as 0, if it can approach 0, but if it approaches 0, e raised to minus delta E divided by t, that becomes infinity, minus delta E divided by t becomes infinity. So we normally doesn't allow that to happen. So the freezing temperature is normally taken as some value greater than 0. And if the temperature is, if the initial temperature is say 1000 degrees Celsius, that is 1000 degree Kelvin, also 1000, and the unit is not required there. In the case of simulated annealing, for temperature, the unit of the temperature is not required. It is just a parameter that controls the number of iterations. So the freezing temperature can be somewhere around 10 also. So then this can be applied to optimization. So then the similarities between the thermodynamic simulation, that is the actual thing, as well as the combinatorial optimization simulations. So the first one is in the thermodynamic system, it is system states, the different system states. In the combinatorial optimization, it is the feasible solutions. And the thermodynamic simulation, it is energy, but in case of combinatorial optimization, energy is equivalent to cost. Then thermodynamic simulation, if it is there is a change of state in the combinatorial optimization, we go to a neighboring solution, that is a change in the existing solution is done. Then in the thermodynamic simulation, the temperature is in combinatorial optimization, it is equivalent to any control parameter. So the temperature is actually a control parameter. Then the frozen state is the heuristic solution. That is when we terminate our algorithm. So actually the simulated annealing is not a single algorithm, but rather a heuristic, because the change in the only thing that we does in this case is that a new solution is generated from the existing solution. That is a change in the existing solution is done. So that particular change is can be done in a multiple ways, in a different ways. So depending on that particular method, the method of changing the solution, the existing solution, the algorithm can be different. The simulated annealing algorithm can be different. So that is why it is known as, it is not a single algorithm, but it is a heuristic strategy. That is, it is just a strategy in which involves many different types of changing the algorithm. So if you can change a mutation procedure, any type of mutation procedure can be incorporated into the simulated annealing. So actually what the mutation procedure that we have discussed in genetic algorithm, in the mutation procedure, what we do is we make a slight change to the existing solution and check whether that particular solution is better or not. So if it is better, we accept it in the case of simulated annealing. And if it is worse, then we accept it with some specific value of probability. So any type of mutation operator can be incorporated into this simulated annealing. That is why it is known as a single algorithm, because for each mutation strategy there are different algorithms. So in simulated annealing, there are several decisions to make and several parameters to set. The parameters can be both generic as well as problem specific. So these several decisions and several parameters, while setting these decisions as well as parameters, we have to consider the type of the problem that is that we are considering, and as well as the size of the problem also. So this is same, that is the decisions as well as the parameters to be set. This is same as in other optimization methods like genetic algorithm or particle zone optimization, etc., etc. The algorithm is, we start with an initial solution. The simulated annealing algorithm is, we start with an initial solution. There is an initial solution is generated. Then we randomize according to the current temperature. That is, we create a new solution. A randomized solution is generated from the existing initial solution. Then we check whether the new solution is better than the current solution. If it is yes, we replace the current solution with the new solution. If it is no, then we generate a random number R. Any random number R is generated. Then we check whether R is less than this probability of delta E. And the probability of delta E, you know that E raised to minus delta E divided by KT. And in the case of simulated annealing, we are not using the K. The Boltzmann constant K is not used. So E raised to minus delta E divided by T is taken. T is the temperature at which this particular change is happening. And delta E is the change in energy. In this case, the change in cost. In the most of our problems, optimization problems, the energy is equivalent to the cost. So the change in cost is taken. So we generate a random number R, then we check whether R is less than probability of delta E. And if it is yes, that is if the R is less than this probability of delta E, then we replace the current solution with the new solution. That is, a worse solution is accepted here. And if it is no, that is if the probability, the random number generated is not less than probability of delta E. In that case, what we do is we doesn't change the solution, that remains the previous solution itself. Then we check whether we have reached the maximum iterations for that particular temperature, for the temperature T. Then if it hasn't not reached, then we again go to the initial step, that is we randomize according to the current temperature. And if the temperature is the number of trials using, or the number of iterations using this current temperature is reached, then what we do is we decrease the temperature by a specified rate. It can be, say, divided by 10. Divided by 10 can be a possible value. Not divided by 10. Divided by 0.9, etc. can be, not 1.1. Divided by 1.1 can be a possible change in, or possible method for decreasing the rate of decreasing the temperature. So otherwise you can decrease the temperature by a fixed value itself, 100, 90, 80, 70, etc. That is also possible. Or you can divide the temperature with a value which is greater than 1. Say if we divide it with 1.1, so the value decreases to somewhere around 9 point something. So that, 90 point something. So that is also possible. Then we decrease the temperature by a specified rate, and then we check whether the lower temperature bound is reached or not. That is, the frozen temperature bound is reached or not. If it is not reached, then again we go back. We go back to the randomize according to the current temperature. If the lower bound is reached, then we stop. That is, stop by outputting the current solution, the current best solution that we have obtained so far. So that is the condition. So we start with an initial solution, then we randomize according to a current temperature, then we check whether it is better or not. If it is better, we directly accept it. If it is not better, then we check whether then we generate if it is not better, we generate a random number and check whether that particular random number is less than the probability value. And if that particular random number is less than the probability, then we accept it, otherwise we reject it. Then we check for the maximum trials. If it is reached, then we decrease the temperature. Else, if it hasn't reached the maximum temperature, then maximum trials, then we go for again randomizing it. So this is the procedure by which the simulated annealing algorithm works. So in this case, you might have noticed that there is only a single solution in our hand, and the most number of solutions that is with our hand at the same time is only 2. That is, The first one is the original solution and the second one is the modified solution. So there will be a maximum of only 2 solutions at the same time. So this is again the algorithm written in what you say in pseudocode format. The same thing is written in a pseudocode format. So the neighborhood sampling is we are doing it at random, and the method in which we generate the neighborhood solution, that differentiates our the one simulated annealing algorithm from the other. So then the simulated annealing allows the probabilistic acceptance of non-improving moves also. In most of the hill climbing type algorithms, we always accepts the best solution only. If there is a non-improving solution is coming up, we are directly rejecting it. But the simulated annealing algorithm accepts the non-improving moves with some probability. And the acceptance probability is dependent on the control parameter T as well as the magnitude of the cost increase. So when delta E, the change in energy, is very small, the acceptance probability is very high. That is E raised to minus delta E divided by T is the condition, that the probability value. So if delta E is very small, so the acceptance probability is very high. When T is high, the temperature is high, again the acceptance probability is very high. But when as T decreases, the acceptance probability also decreases. When T is coming a very small value, the acceptance probability is also becoming less. So in normal case, in most of the simulated annealing algorithms, we are not using this Boltzmann constant K, because it doesn't have a physical analogy related to this K. But T is still referred to as temperature. In simulated annealing, T is the control parameter. T is still referred to as temperature, which is reduced according to a cooling schedule. So that is why we use the term temperature itself. It is actually a control parameter which decides whether how many number of iterations is to be done in a simulated annealing algorithm, and whether a worst solution is to be accepted or not. That is decided by this control parameter T. And because this is computer simulation of a programmatic simulation of annealing process, we use the same time temperature in it. Then we keep the incumbent solution, which is not given in this case. So that is, the incumbent solution is the best solution. We always keep the best solution. So there is a probability that once we accept a worst solution, the best solution that we reached in our algorithm might be lost, get lost, and we will be ending up with a worse solution than the best solution that we accepted. So in some algorithms, what we do is we always keeps the best solution in our hand, and that is another variable we are in another array. We keep the best solution, and then we do the simulated annealing procedure on its own. So this is a type of problem, that is ball on terrain example. That is, there is a ball and it is moving in a it is moving downwards. So what happens is if it is like a hill climbing type search, if it goes like a hill climbing search, then what happens is it will get stuck at this point, or somewhere here or somewhere here. It can get stuck at this position. Why? Because it cannot find out a way to escape from this position. Even though the best position is here, but the ball might not be able to escape from this position. So this is the problem with our normal hill climbing searches, that is the greedy search procedures. But simulated annealing allows non-improving moves also, that is worst solutions are also accepted. So what happens is this ball, this can move this position, or this ball can move to this position, and then again in another move it may be able to go up and reach somewhere here, so that it can again come back to, or it can move to this position. So that is the concept of the simulated annealing algorithm over this hill climbing algorithms. So the decisions that is being done in simulated annealing is two types, as I said. They are generic decisions as well as problem-specific decisions. The generic decisions can be the initial temperature, cooling schedule, as well as stopping condition. So, and the problem-specific decisions can be the solution space, which is our solution space, and how the solution is to be represented. Then the cost function, what is the objective function, etc., etc. Then what should be the starting solution? Then what should be the neighborhood structure? That is how new solutions are generated. So these are the problem-specific decisions. Let's see them one by one. The initial temperature, it must be hot enough. That is, the initial temperature must be large enough to allow free exchange of neighboring solutions and to make the final solution independent of the starting solution. As a large value, it depends on the cooling rate also. That is, if the cooling rate is very low, then we take the initial temperature to be somewhere around 100. Otherwise, you can go for 200 or 300 or even 1000 also is possible. So the cooling schedule is the system should get close to its stable condition at the current temperature before temperature reduction. So that is the condition. The temperature reduction is to be done only after the system achieves a specific state of stable condition. So when the system becomes a stable condition, then only the temperature is becoming reduced. So that is happening in simulated annealing. So the temperature and the probability of accepting non-improving moves should converge to zero. The temperature is converging to zero, as well as the probability of accepting a worse solution is also converging to zero. In order to do this, we have to do a large number of iterations at few temperatures or a small number of iterations at many temperatures. So that is two conditions. One is a large number of iterations at a few temperatures. So in that case, the cooling rate is very slow. A small number of iterations at many temperatures. So that is the cooling rate is fast. So the cooling schedule, a common cooling schedule for one is geometric. That is, T is taken as alpha T. That is the new temperature. The new temperature is taken as alpha times the current temperature, where alpha is in between 0 and 1. So in most of the cases, 0.9 to 0.99 is taken as alpha. So that, as I said, 1.1, T divided by 1.1 can be used as a cooling schedule. So instead of divided by 1.1, it can be taken as 0.9 to 0.99. So it can be multiplied alpha into T. And this implies very slow cooling. If we take alpha as 0.8 or 0.7 or 0.6, that is a very fast cooling. So when we increase the number of repetitions, n rep is the number of repetitions, that is the alpha is the cooling rate, and n rep is the number of repetitions at a given temperature. So when we increase the n rep, the number of repetitions within a specific temperature, the temperature decreases to better exploit the local optimum towards the end. So that is some sort of increasing the number of repetitions as well as decreasing temperature can be done simultaneously. That is, at a higher temperature, the number of repetitions will be very less. The number of iterations will be less. But when the temperature decreases, the number of iterations can be increased. So that way, the number of repetitions can be made dynamic also. So that is n rep, that is the number of repetitions may be dynamic depending on the number of acceptances. That is, iterate until 10 acceptances occur. So that is 10 acceptances means 10 worse solutions are accepted. So in the case of in normal conditions, as the temperature decreases, the n rep also gets decreases in normal simulated annealing. But in a revised versions or in modified versions, in order for the simulated annealing to perform better, it can be changed the otherwise. So n rep should not be much smaller than the neighborhood size. That is it. The repetitions should not be very much smaller than the neighborhood size. The neighborhood size is using a specific neighborhood structure, that is using a specific type of mutation. How many different solutions can be generated? That is the neighborhood size. A neighborhood is like in the case of what is a swap mutation. You might be remembering the swap mutation. One element is changed with, or one gene is changed with another gene. So how many different solutions can be generated using swap mutation? So that is the neighborhood size of that particular neighborhood. The neighborhood can be called as the swap neighborhood because we are doing the swap mutation inside it. So all the neighbors or all the solutions generated from the from that particular solution using swap mutation is within the swap neighborhood, and the total number of solutions that can be generated in this particular way, it is known as the neighborhood size. So another type of cooling schedule is T equal to T plus 1, T divided by 1 plus beta T. As I said in the first case, 1.1 divided by T divided by 1.1. So T divided by 1 plus beta T. Here also beta is very small, implying very slow cooling. So in this case, very less number of iterations are made at each temperature. That is, when the cooling rate is very slow, the number of iterations at each temperature is also low. In general, the cooling schedule is taken in such a way that the rate of cooling is more important than the manner of cooling. That is, whether it is geometric or otherwise. The way in which the cooling is being done is not important, but the rate of cooling is important. To keep the rate of acceptance high at the beginning, that is, we are keeping the rate of acceptance high at the beginning, and towards the end, we reduce it. We reduce the rate of acceptance. The stopping condition. The stopping condition, as T approaches 0, probability of accepting non-improving moves becomes virtually 0. That we have already seen. So we may stop before that, that is after a certain number of iterations, or when, or there is another value is also given, that is T is less than or equal to epsilon. Epsilon is a very small value, epsilon divided by ln, log of modulus of S minus 1 divided by theta. So this is to produce a solution within epsilon of the optimum, that is epsilon value from the optimum. The change in value of the optimum solution and the current best solution will be approximately optimum, and with a probability theta, and the theta will be a probability value, and the S is the solution space, the size of the solution space. So ln modulus of S, that is the size of S, minus 1 divided by theta. So that is a way to stop, a way of stopping condition. The decision criteria can be the validity of the algorithm should be maintained. That is, the when we are taking the problem specific decisions, the condition should be that the validity of the algorithm should be maintained, and the computation time should be used effectively. The final solution should be close to the optimal solution. That is the 3 conditions that you should keep in mind while deciding the problem specific decisions. The solution space, in this case, the condition is that when you are creating a solution space, the infeasible solutions may be allowed and be penalized in the objective function. That is possible, but in most of the cases we avoid the infeasible solutions. So if the solution, if the problem is of type, the permutation type of problem, then we may allow. It is not necessary that we should allow, but we may allow problems where not all the elements are present in our solution. So some elements may be repeating. So that, but in that case, that particular solution should be penalized, or that solution can be repaired also. So then, to reduce the number of iterations, that is the NREP, the N is the number of the number of iterations or number of repetitions. Keep the solution space as small as possible by choosing appropriate moves. So it may conflict with allowing infeasible solutions. So if we allow infeasible solutions also, the solution space will be very much larger. So if possible, apply a series of reductions to the problem without destroying reachability. So that is what you say. If possible, some sort of reductions can be, the solution space reductions can be some specific alleles to specific genes, like some specific values can be fixed at specific locations. So the number of solution space, the different solutions, possible solutions can be reduced. The neighborhood structure, every solution should be reachable from every other directly or indirectly. That is the neighborhood structure. As I said, in the case of swap neighborhood structure, not all the solutions are reachable by one solution, or not all the solutions are reachable from one solution, but doing multiple swap operations, we will be able to reach all the solutions. So then the neighborhood should be small enough to be searched adequately and in relatively fewer iterations. So that is also you should keep in mind while selecting the neighborhood structure, or which type of mutation operation you are incorporating into this simulated annealing. So this is the random generation of a neighboring solution should be fast for effective use of computation time. So the generation, then a new solution should be generated very fast. And obviously the generating a feasible solution can be tricky, so you may be have to do some repair algorithms, or you may have to follow some repair algorithms also in order to make it a feasible solution. So avoid spiky neighborhood topography over the solution space, as well as deep troughs to reduce the number of iterations. So that is what you say in the in our representation of that ball on terrain problem. There were very large troughs as well as very high peaks. Peak was also there. So that sort of neighborhood you should avoid, but we might not be able to understand the different types of neighborhood topography when we apply for a specific problem at first. So what we should do is that the neighborhood structure that we will be keeping should be simple enough to generate. That is the first thing that we could keep in mind while considering this simulated annealing. Then fine-tuning the simulated annealing. The fine-tuning can be done with different experiments for best parameter settings. So there may be different replications you should, which is the best initial temperature, which is the best cooling schedule, etc. In order to find out all those things, you might have to repeat the experiments multiple times. So then monitor the evolution of the simulated annealing algorithm, if possible graphically, for different parameter settings. But it is not possible always. The graphical monitoring of the simulated annealing algorithm is not always possible. But if possible, do it. Then the monitor temperature, cost ratio of accepted moves to rejected moves, and other statistics. So these things also you have to monitor while doing this parameter setting experiments. So then there are some enhancements and modifications also, like functions other than the exp minus delta A divided by t can be used to accept non-improving moves. So that is, there are some values, or some other methods are also there, something like 1 minus delta A divided by t. So that is also possible. Then different cooling schedules can be used in different phases. That is, in the first phase, one cooling schedule; in the second phase, a different cooling schedule, like that. That is, we are dividing the entire algorithm into different phases. Then another condition is using a constant temperature throughout the algorithm. Using a constant temperature may be another option. That is different enhancements. So reheating may be also tried. That is, after some time the temperature has become a specific value, then we reheat, the temperature is increased. So that is also possible. So cooling may take place every time a move is accepted. That is, whenever a Wurtz solution is accepted, cooling may take place. So that is the different modifications that is available in the case of simulated annealing algorithms. So then there are another conditions, like a neighborhood structure may be adjusted also as the temperature decreases. That is, different types of neighborhoods may be used. And again, the neighborhood size may also be changed. The sampling from neighborhood can be cyclic rather than random. That is, a cyclic way of sampling can be possible. So an approximate cost function can be used. The solution space may be restricted, etc., etc. And this is an animation of the simulated annealing, how this particular thing moves. So whenever it is moving somewhere here, the lowest position is in this line, but obviously it was moving to the higher position also, here also. So in this trough, here is actually the lowest positions, but obviously it was moving towards the upper positions. Finally, when it settles down to here also, in the initial temperatures, or when the temperature was high, it was moving to higher values. So that is the simulated annealing algorithm. And that's all. Thank you.